Everyone. Good afternoon, everyone. My name is Svetlana Berzev. I'm president of Serbian Association of Earthquake Engineering, and it's my great pleasure and honor to introduce our speaker today. And the lecture is going to be very interesting for all of us. So the speaker is, as you know, Professor Michael Fardis. He's currently Professor Emeritus at the University of Patras in Greece. He's vice chairman of the Eurocode committee, which is called SAN TC 250 structural Eurocodes. A little bit of his background, very broad and long academic and professional career. Professor Fardis spent a number of years in the USA, where he studied, he got a master's and degree in civil engineering and nuclear engineering, and a PhD in structural engineering from the MIT. And he was a professor there until 1983. He has been very active in journals, as editor of journals. Currently, he's, I believe, or he was editor of Earthquake Engineering Structural Dynamics since 2016, and before that, he was associate editor Bulletin of Earthquake Engineering, and editorial board member of many other journals. He's in the last 10 years or so, he's really well known and recognized for his great contribution to the development of Eurocodes. Since 2013, he has been on the chairman or vice chairman of development of the structural Eurocodes. And he was also he led the development of the first generation of Eurocodes, Eurocode 8 from 1999 to 2005, and that is Eurocode, which, as you know, we've recently introduced in Serbia, first generation of Eurocodes. Here in Serbia and in the region, and I believe in many in other regions as well, he is well known also for his books, which explain Eurocode and its application, and are very popular among engineers and students and academics, and they're the main source of knowledge or understanding for Eurocodes. So without further ado, I would like to invite Professor Fardis to start with the lecture, which is going to be very useful for all of us in the light of understanding Eurocode and its challenges. And thank you very much, and please go ahead.
Thank you, Svetlana. It's my great pleasure and honor to be with you today. Thank you for the invitation. I see this presentation as, let's say, the first half of my interaction with the Serbian community of earthquake and structural engineering, since I hopefully will come to Belgrade in September and give live another lecture on more or less the same subject, not the same content, but the same general topic. So I see this talk as let's say, the first half of this interaction with you, with your community, and whatever I did not have time to include in today's lecture, and whatever comes up, I will have the opportunity to present to you in September. Now, my presentation is long. It has a very large number of slides, which I will not go through in detail today, but it will be available to you through your association, and hopefully will prove useful. I will focus on on a few issues, and then we'll have the opportunity to interact through questions and answers after the end of my presentation. My presentation is essentially consists of three parts. First, I will give an overview of the provisions of Eurocode 8 for concrete buildings, focusing on key issues in the evolution from the current first generation to the new generation, which is currently under development. Then I will give more emphasis on the issue of walls and wall systems in buildings, because some of the Serbian colleagues have told me that this is an issue which is sort of hot in Belgrade, especially today, because of construction of high-rise buildings with wall systems and wall core. And then I will go quickly through an application to a building of the current generation Eurocode 8 to a building with 6 stories and 2 basements with walls. I was hoping that I would have time to repeat this exercise for that building using the current draft of the second generation Eurocode 8, but I have run out of time. It proved to be a more time-consuming and challenging exercise, but I promise that I will finish it soon, and I will have the opportunity to present to you the difference in the outcome and the experience from the application of the second generation of Eurocode 8 to the same building, and possibly enrich it following today's interaction with you. Okay, starting on the first part, the timeline of the various generations of the Eurocodes is shown in this, summarized in this slide. There was a period in which the pre-standards, the ENV versions, were developed from 1975 until 1992. These were shorter and preliminary versions, which were never applied in practice, but provided the ground for the real Eurocodes, which were drafted starting from 1998 and completed in 2007, and made, let's say, compulsory as standards in 10 countries in 2010. Right after their enforcement, the effort drive towards the second generation of Eurocodes started in the period between 2012 and 2014, let's say. And since 2014 until today, and for 2 or 3 more years, the second generation will be developed and completed. Hopefully by the end of 2025, all about 65, I would say, parts of the second generation of Eurocodes will be voted, hopefully positively. And then by I believe March 2028, they will be made again compulsory as standards by withdrawing the conflicting standards, which means the current first generation. So it's a long process. By coincidence, the 18 years have passed from the end of the ENV period in 1992 to the enforcement of the first generation in 2010, and again 18 years to the enforcement of the second generation. So this turns out to be the period of in the development of the various versions of the Eurocodes. So one can expect that the second generation again will be applied for before being replaced by the third one for almost 20 years. Now, the objectives of the second generation are summarized in this slide. One major objective is to reduce the number of nationally determined parameters, which provide flexibility to countries to choose their preference for some key parameters or options allowed by the Eurocodes, not freely, but with significant flexibility. But this is against the harmonization of structural design standards in SEN countries. So there is a strong will and a strong, let's say, pressure to reduce their number. And in the second generation, indeed, they have been reduced by more than 2/3 from the current number. Second major objective is to improve ease of use by improving clarity, simplifying certain routes, limiting alternatives if possible, etc., and avoid overlapping. Of course, the third issue is to expand the scope and fill the voids, which essentially gave the opportunity to update the content of the Eurocodes and enrich it according to the current state of the art. Another objective is to shorten the Eurocodes, to make them shorter for ease of use. But in fact, instead of becoming shorter, they become longer because of the addition of considerable new material. So this slide shows the current first generation in black and the additions in beyond the improvement of the current Eurocodes, the addition of new ones. There will be a new Eurocode on structural glass, on structures made of structural glass, and there will be technical specifications which may develop soon into Eurocodes on fiber-reinforced polymer structures and membrane structures. In addition, there is a significant effort to add provisions and parts on assessment and retrofitting of existing structures, which exist currently only for Eurocode 8, the seismic design Eurocode. But the idea is to add similar provisions to all material Eurocodes, and as well as to the to fundamental Eurocode, the N1990, which is, let's say, the constitution of all Eurocodes. And this is well progressing. In addition, there is an effort to improve whatever has to do with robustness of structures. Now, the Eurocode 8, the Eurocode for earthquake-resistant structures, has currently 6 parts, and it will have 6 parts, but there will be restructuring with merging of what is now parts 4 and 6, which has to do with, let's say, industrial structures, non-building and non-bridge structures, and the splitting of part 1 in 2 parts, one containing the general rules applicable to all types of structures, as well the provisions for the seismic action, and another separate part devoted to new buildings. This is the structure of this, the current part one with the general rules, seismic actions, and rules for buildings. Of interest to us today are the chapters shown in red, which include the general provisions and those specific to concrete buildings. And this part will, as I said, will be split in two. The first one, the contents of the first one are shown in this slide. They have the general requirements, the whatever has to do with the seismic action, and with general analysis and verification approaches, as well as the formation criteria and strength models applicable to all types of structures. This part has progressed a lot and is currently under final editorial polishing, and will be put in public inquiry, as it's called, for comments by national member groups later this year, in September, October. And hopefully there will be a vote on it next year, along with part 5, which has to do with the geotechnical structures. The other parts will follow. And these other parts will include this part 1-2, which is almost ready, but it has to await for the other material Eurocodes for concrete, steel, composite, timber, masonry, or aluminum structures, which are still under development. Some of them are less progressed than Eurocode 8, but Eurocode 8 has to be consistent with them, so it has to await their finalization and stabilization. So this part may be voted rather late. The more detailed table of contents on for concrete buildings, whatever refers to concrete buildings in this part, or for new buildings, is shown here with the sub-chapters, let's say, for concrete buildings. Now, coming to the substance. In the new Eurocode, in principle, there are 4 performance levels, which are called limit states. 2 serviceability limit states. One is the operational limit state, and the other is for damage limitation. And 2 ultimate limit states, significant damage and near collapse. Other parts of Eurocode 8, namely part 3 on existing structures, cover in more detail possibly all of these 4 limit states, but part 1-2, which refers to new buildings, focuses on just 2, the damage limitation limit state and the significant damage limit state. As shown in this slide, which is similar to what we have now in the current generation Eurocode 8, with emphasis on significant damage and damage limitation under about 500 and about 100-year earthquake, respectively, and hidden and without spelled out and specified earthquake level associated with it. We have also collapse prevention under a very strong and rare earthquake through application across the board of capacity design. So we have essentially 2.5 limit states currently and in the new generation. A detail concerning reliability differentiation. What is currently called importance factor and importance levels, etc., will be called in the future consequence classes, and symbolized by CC, consequence classes 1 to 3A and 3B. And depending on what type of fielding we have and its importance and the consequences of its failure or damage, we will have a different level of seismic action by application of a multiplicative factor shown on the right-hand column or at the top table and at the fourth column of the second table, on the 475-year design seismic action, which is called a reference seismic action. But in the second generation, we will have spelled out importance factors or performance factors, as they are called now, and return periods for all combinations of consequence classes and limit states, as shown in this slide. Some terminology. As I said, the reference seismic action is the one for which new structures of importance or of ordinary importance or ordinary consequence class are designed, and its reference return period is a national return parameter. It is up to the countries to choose, but the recommended value is 475 years, which corresponds to a 10 probability of exceedance in 50 years. Talking about seismic action, this is the list of the standard ground types, essentially hard rock, stiff soil, firm soil, soft soil, and special types of soils, characterized on the basis of the shear wave velocity in the top 30 meters of the ground, VS30, or if that is not available, through the SPT blow count number or the shear strength of the soil. In the new Eurocode, the standard ground types will be more in number, but slightly more in number, but not much different in substance. But the classification will depend not only on the shear wave velocity, but also on the depth of the soil deposit, which affects the ground motion at the surface. An important change is in the characterization, in the specification of the seismic action, which is currently described by a single parameter, the peak ground acceleration on rock. This is the reference parameter to which the elastic response spectrum for 5% damping is anchored, and which is supposedly given in national zonation maps. It will be replaced by two parameters on rock: the short period spectral acceleration for 5% damping, S sub A, S sub alpha, and the 1 second spectral acceleration, again on rock, S sub beta. And instead of the two standard spectral shapes with parameters given in the national annex depending on the seismicity, etc. of the site. This is the current, let's say, the recommended characterization of the seismic action with the parameters, the soil factor S, the corner periods T sub B, T sub C, T sub D for the two types of seismic action, one for relatively large earthquakes dominating the seismic hazard, type 1, and the second for low magnitude earthquakes dominating the hazard. This is type 2. Essentially, type 1 is for the moderate to high seismicity regions. Type 2 is for the low seismicity regions, where the hazard is controlled by, let's say, near field earthquakes. So, so instead of this type of spectrum, we will have a more complex spectrum described by more parameters. The shape may look a bit frightening, and the number of parameters, but I am sure that all of us will get used to it. Now, for the first time, the second generation Eurocode includes European hazard maps, at least in an informative annex, which to which some countries object, and I'm not so sure that this informative annex will stay. But this informative annex, as well as the wealth of information which is behind it, will be a very useful basis for countries to develop their zonation maps. So again, these are the 475-year return period parameters. For the short period spectral acceleration in this map, and for the 1 second spectral acceleration. And you can see that for Serbia, the short period spectral accelerations are in the northern part around, let's say, 0.2 G, which means 0.08, about 0.08 G in terms of PGA. And for the south of Serbia, they are around, let's say, 0.3 for the spectral value, which means about 0.12 in PGA terms. A very mild case of moderate seismicity, I would say. And these are the values for the 1 second spectral accelerations, much lower, because Serbia, like other low seismicity regions, are dominated by near field earthquakes, which and small magnitude ones, which attenuate faster with distance. But you can see in both maps the very high values in the Vrancea region in Romania. And these are deeper earthquakes, which are rich in longer periods, and sometimes may affect, they attenuate slower, and they may affect tall buildings at long distances. This is an issue possibly for parts of Serbia. Okay, this again complicated slide gives the nonlinear amplification of spectral values with level of seismic action as a function of the shear wave velocity, etc., etc. Much more complex, let's say, presentation than the current one, which is so simple that it is simplistic and it is obsolete. The current description of the seismic action, I would say, is well behind the state of the art and the current level of knowledge in Europe. Going now to design. I will not talk about displacement-based design based on nonlinear analysis, which is an option given allowed in the first generation and given full support and more details in the second generation. I will focus only on ductility-based design using the force reduction factor, what is called in Europe behavior factor Q, which divides the elastic spectrum to convert it into a design spectrum. So on the base of the value of Q, of the behavior factor, and the ductility level, both versions, the current and the new, have three ductility classes. High, medium, and low in the current situation, 3, 2, and 1 in the new one. The change in numbering is for convenience to countries for which the letters H, M, and L don't automatically relate to high, medium, and low. So we will have 1, 2, and 3, but essentially the meaning is like low, medium, and high, although the substance is different. The Q factors have decreased from the first to the second generation, but the requirements also for ductility, detailing, materials, capacity design, and the complexity of the design have been reduced compared to the current first generation, because it is recognized that ductility class H, as it stands now, is neither so useful nor frequently used. So it is like an academic, say, option, not very useful in practice. So it has been replaced by ductility class 3, which is closer to ductility class M currently, and then ductility class 2 is essentially in between current ductility class medium and low. The behavior factor has been split in 3 factors. One, due to overstrength, equal always to 1.5, and considered to be available irrespective of detailing and any ductility in design. A second factor, Q sub bar, which accounts for the redundancy of the structural system and the possibility of redistributions. And the third is accounts for ductility. I will go back. Okay. I will go back to this slide after showing the values of these Q factors, current ones for the 3 levels ductility classes. Ductility class L, which is recommended only for low seismicity regions, has a Q factor of 1.5 always. And ductility class H reaches high values, especially for frame and wall systems which are included in the last row. Two special cases are the inverted pendulum systems, which are those which have the most of the mass concentrated at the upper third of the height, or depend on elasticity only at the base of one or a few elements. And another special case, what is called torsionally flexible structural system, which may be of interest to buildings with a core of walls in the center and frame members and columns which contribute little to the lateral force resistance closer to the perimeter. These are typically torsionally flexible in the sense that their fundamental period, the mode number one, is torsional. And these are sensitive to accidental eccentricities, to torsional components of the seismic action, and to other factors for which design does not account for. So they are heavily penalized in the current generation, but they are less so in the new generation. We will come back to that soon. Both in the current version and in the upcoming one, an important safeguard against collapse for frames is the capacity design verification of columns against plastic hinging and the promotion of plastic hinging in the beams, represented by the inequality at the top of this slide. In the current version, this satisfaction of this condition is required for all frame or frame equivalent dual systems of ductility class M and H. In the new second generation, this condition, the application of this condition is less universal in the sense that it has been replaced by a check at the story level shown at the near the bottom of this slide for ductility class 2 frame or frame equivalent systems. Essentially, this more general check at the story level means that plastic hinging at both ends of all columns in the story is allowed, provided that it does not lead to failure of a single column in the story. This is the meaning of the presence of the plastic rotation capacity theta U minimum at the end of the condition shown near the bottom of this slide. So these are the values of the behavior factor in the coming generation, in the second generation, for the three ductility classes, or at least for the two of them, DC2 and DC3. For DC1, the Q factor is always equal to 1.5 because Q sub bar and Q sub D are equal to 1. the maximum values achieved when one chooses DC3 and a ductile structure system are lower than in the current version. So from that point of view, the one might say that the second generation is less economic. I'm not so sure because ductility costs, detailing with dense stirrups and other factors which ensure ductility is expensive, although one may save money on longitudinal reinforcement. So the ductility class, whether it is 2 or 3 or M and H, normally does not affect either of the overall economy of the structure or the safety it provides on average terms. So one should not be should not focus on the reduction of the Q factors. This does not have very serious implications on the economy. The current first generation does not pose very strict restrictions on the choice of the structure system or the ductility class. The only restriction is the discouragement of ductility class low for cases other than low seismicity, which means PGA at ground surface above 0.1 G, or spectral acceleration short period range above 2.5 meters per second square. Now, in the coming version, there will be more restrictions on the use of ductility classes and various types of structure systems, depending on the seismicity, are shown near the bottom of this slide. Especially for flat slab frames, which are not allowed for essentially above 0.2 G peak ground acceleration, and also for the use of wall structures in DC3. Both the current version with very minor differentiation require capacity design of beams and columns in shear, recognizing the possibility that blasting hinges may form either in the beams or in the columns, depending on whether the columns meet the capacity design condition in flexure. The overstrength factors gamma RD, which are applied on this in this calculation of capacity design shears, are a little bit reduced by 10–20%. So this makes the capacity design in shear a bit more economic. Now, in both cases, in the current generation and the new one, there is a link between behavior factor Q and ductility factor, which in the case of the current generation is expressed through the curvature ductility factor mu sub phi, which is related to the Q factor through the relations shown at the top of this slide, depending on fundamental period. These are approximate relations, not of general applicability, which I might say work on a bit on the conservative side. They are rather safe-sided. Their implementation is through the maximum reinforcement ratio in beams at the top reinforcement at the support sections of beams, through the relationship shown near the bottom of the slide. This maximum ratio of tensor reinforcement at the top essentially protects the beam from early crushing of the concrete at the bottom flange, while for columns and ductile walls, this curvature ductility is achieved through confining reinforcement, which is estimated through the relationship shown near the top of the slide. This is a rather simple relationship, which gives, I would say, reasonable results. In the second generation, this the link between ductility and behavior factor is achieved through the chord rotation ductility factor, and it is more direct and more transparent. The detailing should be such that the chord rotation ductility factor, defined as the ratio of the chord rotation at the significant damage limit state to the chord rotation at yielding, divided by an appropriate safety factor, corresponds to the value, to the component of the behavior factor due to ductility. And the Eurocode in part 1.1 gives explicit relations to compute both the chord rotation at yielding. These are the relations given in this part 1.1, as well as in the same part for the plastic rotation capacity of members with rectangular compression zone, columns, beams, walls, rectangular or non-rectangular, etc. This is a complicated but relatively accurate relationship, which is included in part 1 of the Eurocode 8. Now, coming closer to the end of the first part of my talk, and the longer one, another major change in the second generation, which affects mainly walls, is the calculation of the shear resistance, which has to follow always the provisions of Eurocode 2, which are summarized for the current generation of Eurocode 2 in this slide. And their counterparts for the 3 ductility classes in Eurocode 8 are shown in this slide, with variations depending on whether we have a beam, a column, a wall, or a short wall, a wall with a low shear span ratio. Always variations of the basic, of the fundamental model in Eurocode 2. In case of ductility class H beams, taking in the strut inclination always at 45 degrees. The same also for ductility class H walls, for which there is also a 60% reduction in the shear resistance due to diagonal compression in the concrete, web compression. This is the VRD maximum, which is, in the case of walls of ductility class H, 40%, just 40% of the normal value. This essentially makes this design of ductility class H walls close to impossible. Coupled with the increase of shear demands due to higher mode and overstrength effects in walls, which increases by several times the shear forces in walls compared to the values from the analysis, I would say that it is practically impossible to design a ductility class H building with walls. With frames, it is feasible. With walls, it is impractical. Fortunately, the new approach in Eurocode 2, which is a bit more complicated, but much more economical, relaxes very much the conditions for cyclic loading and for the high ductility level. This new approach is more complicated in Eurocode 2 in that the shear capacity due to diagonal compression in the web is made a function of the longitudinal strain at mid-depth of the member, which has to be calculated as a function of the bending moment and the axial force, and then values of the strutting inclination and the shear strength are computed by iterations. It is not an easy procedure. It is an iterative one. Now, it happens that with a reduction of 60 by 1.6 of the monotonic shear resistance due to diagonal compression in the web, and with a very easy estimation of the inelastic longitudinal strain by multiplying the elastic moment by the Q factor used in the design, one has very good agreement with experimental results for cyclic loading for all types of members. So with a very minor modification of the new Eurocode 2 approach, one has a general procedure applicable for all ductility classes 1, 2, and 3 in seismic design, which is much more economic than the present one for walls. I finished this part by just showing, not going in detail, into tables which list the detailing provisions of the current Eurocode for ductility class H, M, and L for beams, columns, and walls, separately for longitudinal and for transversal reinforcement. The prescriptive detailing provisions of the second generation are shorter and less complex than those of the current generation. This is clear from the fact that the tables for the current generation, for example, this one, is much longer than the tables for the new generation. So these tables summarize in a friendly way all the detailing provisions, minimum, maximum, and special design provisions for these three types of members: beams, columns, or walls. The provisions for walls concerning the current version cover 1, 2, 3, 4, 3 pages. The provisions for walls for the new generation is just 1 page, much shorter and simpler. So we hope that in the future the use of walls will be easier and more friendly to the designer and more reasonable in terms of cost and without loss of safety. Coming now to the second part of my presentation, I will say a few more things about walls. There are 2 types of walls in Eurocode 8. Ductile walls, which are the usual ones, and large, lightly reinforced walls. The large walls are popular in France. So I will show you examples of large walls, not from France, but from Greece, from Patras, from other Athens, other parts of the country. These are walls which physically cannot develop a plastic hinge at the base. And they don't need that much reinforcement. So they have special design provisions for them. The ductile walls are designed and detailed for developing a single plastic hinge at the base, and they are severely over-designed in shear against not only the overstrength between the at the base between the capacity and the moment from the analysis, but also for the higher mode effects on shear, because a wall keeps vibrating above the base even after development of the plastic is there, and the shear forces do increase considerably. So there is a considerable magnification of the shear forces compared to those from the analysis in upper stories. This magnification is kept and made even more demanding and severe for ductile walls in the new generation. But fortunately, the relaxation of the resistance provisions makes these walls easier to design in the new generation. Everything from the envelope of shear forces to the envelope of moments for the design is on the safe side for walls, for ductile walls. Aiming and making sure that inelasticity will develop only at the base of the wall. By contrast, for large walls, there is an effort to avoid overstrength, to have as little strength as the analysis requires. And there is very little additional or minimum reinforcement. Even horizontal, these provisions go to the point that they allow avoiding horizontal reinforcement at all. One can design, under certain conditions, large walls with only vertical reinforcement and horizontal reinforcement only at very, very few places. This may sound strange and against the provisions of Eurocode 2, which require horizontal reinforcement against wind, against any type of action for all types of walls. So if you design, according to Eurocode 2, a wall for wind alone, you should place horizontal reinforcement. If you design it for earthquake, under certain conditions, you can put no horizontal reinforcement. The reason is that there are 2 reasons for that. First of all, The earthquake is a dynamic action. Even if a 45-degree crack forms in a story during the earthquake, it will open up, but not uncontrollably. When the motion reverses, the 45-degree crack, not restrained by reinforcement, will close. So there will be no collapse. Second, a large wall is large enough to force the 45-degree cracks intersect floors, which are normally every 3.5 meters. And then the floors with their reinforcement act as horizontal ties and control the opening of the crack. So for these reasons, these large walls are allowed in Eurocode 2 to have very light or very little or even no reinforcement for certain types of reinforcement and under certain cases of seismicity. So these are the provisions for in detail of large walls. A final point, which has been raised also by questions by some of the attendees today, concerning composite walls with composite section consisting of more than one rectangular parts, T, L, U, double T, or even more complex sections, which are common in high rise buildings or tall buildings as wall cores. Frankly, we don't know very much about the earthquake behavior of this type of walls. There are no realistic size tests on them. There are many questions about them. And the Eurocode addresses them, I would say, not going by not going to the heart of the problem, but by just requiring that the wall will be considered as a single prismatic member with an integral section composed of various rectangular segments, and applies to them the same type of modeling, design, and detailing as for rectangular walls with minor modifications. If one wants to be a more sophisticated and accurate and model these type of walls with shell type of finite elements, there are absolutely no tools in Eurocode 8 for the dimensioning and detailing of these walls for ductility. So if one chooses to go that way, it's better to design such walls for elastic behavior. As a matter of fact, they don't need much ductility. But even though when one applies elastic analysis and models those walls with shell finite elements, the new generation of Eurocode 8 gives strain limits listed in this slide. They are, strictly speaking, not applicable to such a case. They have been developed and address the calculation of ultimate curvature for use with the plastic hinge length for prismatic members. So it may be far-fetched to apply these strain limits to walls with composite section modeled and analyzed with shell-type finite elements. So this is a dark area. I finished my the part on walls by showing you some slides on damage of walls in past earthquakes. This is a building with walls at the ground story, and you see the failure after the collapse of this building. These are typical pictures of shear failures, which are very, very common in walls in buildings. I have seen many, many shear failures in walls, very few flexural failures. All these are shear failures. This is a shear failure, but a sliding type of shear failure at the base of a wall at the construction joint. And this is the only case I have in my collection of slides from damage in earthquakes in Greece, where in addition to a shear failure, there is also flexural failure in both in tension and compression at the base of a wall. The walls have many advantages, and they have been used in many parts of the world. They have been very popular, and sometimes they have been overused. And one example is in Central and Latin and South America. Following the very good performance of wall buildings in Central American earthquakes, they have become very popular throughout South America. But in the recent, relatively recent earthquake in Chile, which has hit severely Viña del Mar and Concepción, many buildings with walls as their sole lateral force resisting system have shown spectacular cases of collapse. Some of these failures and partial collapses are shown here. These are typical framing plans of these buildings. These are in Chile, partition walls and exterior walls have been replaced in high-rise construction by thin concrete walls. As you see here, all these black parts in these framing plans are walls, very thin ones, about 15 or even 10 centimeters thick. Other examples, and one case where the building shown on the left has collapsed, as you see on the right, and you see the framing plan at the bottom. Similar cases. Heavy reinforcement, but very little confinement, because even if you place confining reinforcement with such a small thickness compared to the length of the wall, and such a high axial load because of the height of the building, it is not feasible to achieve confinement over a significant part of the section. So all these walls failed spectacularly. You see all these failures, which have very clearly the signature of high compression. I would not say, I wouldn't call them shear failures. They are more compression failures due to combination of bending and axial load. And it's clear that there was no confinement in these walls. This may have to do with the way these walls were designed and detailed. So one has to be careful with overdoing it with walls. In parts of South America, these thin walls were constructed, maybe they are still constructed, with a single curtain of reinforcement at the center of the section, not with two curtains on two sides. Examples to be avoided. Now, I will finish with just showing, without going in detail, an application of the first generation Eurocode to a six-story building with two basements. This so-called Lisbon example, because it has been used as the basis of a workshop about 15 years ago in Lisbon. And the workshop has built on this structure and this design for the application of this first generation of Eurocode 8. These are the design parameters: C25, S500, peak ground acceleration on rock of 0.25 G, ductility class medium. The building is clearly a wall system in the y direction, in the vertical direction, as you see it on these slides, and nominally a dual wall equivalent system in the other direction, in the horizontal direction on these slides, because walls take 65%, just a little bit less than 65% of the base shear. If they were 5 centimeters longer, this would have been also clearly a wall system. These are the periods from Rayleigh quotient and these corresponding spectral values. And these are the fundamental modes, translational in both horizontal directions. The third mode is torsional. The interstory drift ratios and diagrams for bending moments and shears in the various planes of the building. I will not, you will have the full presentation shared, so I will not go in detail in this. I want to point out that the perimeter walls of the basement, two-story high, were modeled as and dimensioned as deep beams on elastic foundation, modeled with sub-elements of about 1 meter length. Each span of the perimeter walls split into 5 or 6 such sub-elements, all of them on vertical Winkler type springs, which however have a shear stiffness appropriate to model the shear stiffness of the perimeter walls in a vertical plane. And the perimeter walls, both for gravity loads and seismic loads, were designed and detailed as deep beams according to Eurocode 2. In this example, there are examples of detailed calculations of strings of beams at various stories of and the amount of reinforcement, longitudinal and transverse, at all levels in all beams. There are also lists of the reinforcement in the columns. These are cross sections of the columns and their reinforcement. And for a single representative column, detailed tables with all their steps for their design according to the Eurocode 2 and Eurocode 8. Okay, all the details for this column, a single column, in all its stories. There are more detailed results for the 3 types of walls: the rectangular walls at the perimeter, with the envelopes of moments and shears, and the cross sections. The rectangular walls near the center of the plan, which goes through the 2 basements as well, with its this moment and shear envelopes, and the detailed numerical results. And finally, the C-shaped or U-shaped wall. Here the details of the reinforcement refer to one half, the left half of the wall. It's not an L wall, it is a U-type wall, but only one half of the section is shown, along with the biaxial moment diagram for the resistance and the points for the demand. And finally, example of the reinforcement in the basement walls considered as 2-story tall deep beams with their reinforcement, which is controlled essentially by the provisions of Eurocode 2 concerning crack control in beams. The reinforcement required at top and bottom for bending is significant, but what is more interesting is the amount of reinforcement required for crack control all along the 2 stories of these basement walls. There are also calculations for 1 footing of an interior column, etc., and corresponding drawings. I do hope that by the time we get together again in September, hopefully in person, I will have this example done also with the 2nd generation, and I will be able to draw some conclusions. And with this, I want to end my presentation. Sorry that I took longer, and sorry for tiring you so much. I hope that we have time for questions.
Thank you very much, Professor Fardis. We are very grateful to you for sharing your knowledge and wisdom of the Eurocodes. It would be great if you have time for some questions, as we discussed. As we discussed, there are, and I missed to mention that at the beginning to all participants, is that the question they can ask questions in the chat, those who haven't asked questions, and we have a few questions that we forwarded to you already, and you mentioned that you might have answers, have looked at them, or I'm not sure if you've written answers, but maybe we start with those. In the meantime, the other participants who have questions may write the questions in the chat, and if needed, we can also ask the questions. Maybe it's easier in chat. And Professor Branko Milosavljević is also here. He is also going to help moderate this part. He's also in the Branko. Maybe you can also use a video to see you. So can you please let us know how you would like to proceed? Do you have answers to questions, or you would like us, the colleagues, to send you those same questions in chat, or you would like to share you or us to share the questions that have already been asked?
The faster would be to share the questions and the answers. So let me stop sharing for a minute to in order to find the file with
Thank you for taking time to write the answers also in this busy time. We appreciate that.
Okay, I now have in front of me the questions and the answers. Let me go back to sharing. Okay, I have to close the presentation first. Okay. Now I hope you see.
Yes, we can see. We can see the document and the question.
Okay, let me increase the size. Okay, first question or comment. It says that essentially the northern part of Serbia with Belgrade included is a low seismic area with a peak ground acceleration of 0.10 g, and some of the Eurocode 8 rules can be relaxed, etc. Yes, in fact, the case is at the border of applying the option of the critical cell, but at least according to the Eurocode rules, this is an option to be exercised by the national annex, by the national authorities. It is not up to the designer to relax the rules. Okay, this has to be decided by the national authorities through the national annex. Okay, of course, national authorities have the authority to specify whatever they want through regulations. Standards are different from regulations, and regulations can, like presidential decrees, etc., can apply in parallel or overrule the standards. So the national authorities can do whatever they want. Designers cannot by themselves do it. Okay? Now, in the second generation, there will be more freedom, possibly even for the designer. Okay, to how to treat these low seismicity cases. Okay.
Thank you for this explanation, and I believe there are a couple of more questions within that same question or sub questions, and then maybe we can ask the colleagues who all asked the question if they have any comments on what you said, or they would like to further ask.
Yeah, okay. The second question, whether seismic hazard will be an additional criterion defining special measures regarding the detailing. Yes, as I touched on this issue during the presentation, but in general there will be more flexibility and additional options depending on the seismic hazard and importance.
Thank you.
Okay. Well, the other question asks whether one can avoid designing for earthquake at all for peak ground acceleration up to 0.10 G. Again, this is something that the National Annex could allow. Personally, and most people I know in the earthquake engineering business would not advise such a practice. Because even in low seismicity regions, small magnitude earthquakes can cause very high peak ground accelerations and short period spectral accelerations, which may penalize, may hit stiff buildings. And if they have absolutely no ductility and no design for earthquake, damage may be heavy and collapse could be may not be ruled out. So I wouldn't advise not doing any seismic design at all for peak ground accelerations around 0.10 G.
Thank you very much. And we have a very limited statistical values about our earthquakes in the past. So that is one more reason for not going that route. So maybe if in order to give people more interest of the more opportunity to ask questions, maybe if you can go over the other two questions, and we see some more questions in chat. So if you can, thank you very much. If you could maybe go on to the next question.
Yes, well, the next two or three questions refer to the composite walls, to which I also say paid some attention in the presentation. I repeat that we don't know much about this type of walls. It is virtually impossible to test these walls in the laboratory at a realistic size. And we don't know much. Analysis can give whatever the modeler wants, but nature decides otherwise. And the only way we can know what nature thinks is by doing tests or observing the behavior in earthquakes. And unfortunately, we don't have too many observations or data for this type of walls. I have shown you the cases in Chile and the very bad behavior of some of these type of walls if they are very thin. I would be very careful about them. Concerning their treatment as an assemblage of rectangular parts, I would say no. I don't know exactly what this question means, but if I understand it correctly, if you treat a composite wall as a assemblage of rectangular parts and design them as such, you may be doing a serious mistake. Okay. Concerning possible simplification of the approach for composite wall sections, I don't think that one can simplify the treatment of this case very much, because there is no ground to base such a simplification with confidence. How do we apply the moment level requirements for composite wall sections? As I said, the only case addressed in Eurocode 8 is walls modeled and designed, detailed as a single prismatic cantilever element with various stories. And the moment envelope provisions apply to that case. The last question concerns coupling beams and design of walls and shear. The detailing provisions for coupling beams currently refer only to ductility class H coupled walls. And they are a challenge to apply, not only in design, but mainly on the site. In the second generation, the provisions are not so detailed for coupling beams, and they just mention the possibility of applying strut and tie models, which may imply introduction of diagonal column-like elements along the struts as a possibility. It says that the strut and tie approach may be used. Other approaches, including the conventional type of reinforcement with horizontal longitudinal bars and vertical ties, are acceptable. The final question points out that essentially in ductility class M walls, both coupling beams and the walls themselves, the provisions for shear do not have any special reduction due to the cyclic nature of the loading. Yes, indeed, they don't. And this is not always safe-sided. As I said during the presentation, the new approach, which is universal, the same for ductility class 2, 3, or 1, and essentially the same as in Eurocode 2 for monotonic loading, covers in the similar way all types of walls for all ductility classes, and offers a much better balance of safety, economy, and practicality.
Thank you. Thank you for these answers. We can see 2 more questions in chat. Are you okay to answer them now, or you would prefer to answer?
Let me see them.
The first is related to bridges, and the other is related to stiffness. One is by Goran Milutinovic. Can you see the chat, or you would like?
I can see it. Why
maybe if you go first by Goran Milutinovic.
Well, okay. I'm not so sure that the behavior factor for bridges is smaller than for buildings. Please think of single pier bridges integral with the deck, monolithic with the deck. According to Eurocode 8 Part 1, this is a typical inverted pendulum structure because it has most of the mass, if not all, at the top. And for for buildings of this type, Part 1 gives a value of a Q value of 1.5 essentially for regardless of ductility level, ductility class. By contrast, for bridges, we have higher values of Q factors, although one cannot deny that this type of construction looks very much like inverted pendulum. So this is one. Second is that now in the second generation, the Q factor values for bridges have not decreased, but those for buildings were reduced. So there's better balance between the two. Now, concerning the shrinkage, shrinkage is considered in Eurocode 8 for bridges only concerning unseating of the deck due to combination of shortening of the deck due to shrinkage and creep and seismic movement. But in general, the internal forces which are due to imposed deformations, be it temperature, be it settlements, or shrinkage, their effects on internal forces disappear when inelasticity due to earthquake is dominant and controls. So the effect of shrinkage on internal forces is overshadowed by the effect of the earthquake. Is that okay?
So
I hope, yes. Let me read the second question.
About stiffness reduction.
Yes. Okay. Yes. Well, the 50% of uncracked stiffness approximation to the secant stiffness to the yield point is retained, but more emphasis and more tools for the calculation of the effective stiffness are given in part 1 now for general application for all types of structures existing or new. The problem with the application of these tools is that one has to know the reinforcement to calculate the effective stiffness. And for new construction, you don't know the amount of longitudinal reinforcement at the outset. So one has to do iterations, and the 50% of uncracked stiffness approximation is conservative, is safe-sided if we talk of force-based design. Okay, so this remains more or less the same, but if one wants to use the effective stiffness as calculated with the tools given in Eurocode 8, these tools are enriched and their validity is strengthened.
Thank you very much. Do we have any more questions from the, it doesn't have to be in chat, maybe one last question if there is any or comment. We don't have any more questions in chat, and thank you so much for giving detailed answers to each and every question. That is greatly appreciated. So any more? Mladen Milicevic. Okay, let us see. One more question from in the chat, if you don't mind. Let us see. Do you want to read? It is the last one now. Let it be the last one for this. As I said, we'll continue in September, but maybe this one, if you can. Podactyl walls.
Well, I will read the question. Due to architectural requirements, it is not unusual that in later stages the need for a larger opening in walls at ground floor arises, door in plastic is reason. If it is the case for dominant primary structural wall, what parameters criteria should we follow to make that wall ductile? And is there any limit or guidance for acceptable size, shape of opening perforation in plastic hinge regions? I wouldn't advise that practice. The second generation gives much more detailed and educated answers to the issue of openings in walls and gives more specific guidance for them. there are experimental data on the effect of openings, but I would be careful. I am not so sure that one can open a larger opening, as the question says, in later stages when the need for it arises at the ground floor. If I understand it correctly, and this means that in a wall, one wants to enlarge or open a large opening for use for architectural reasons, one has to be careful, and the implications have to be considered cautiously, I would say.
Thank you very much. Again, one more question about thin walls in Chile. Would the thin walls in Chile building have failed the normalized axial force limit if calculated according to Eurocode 8?
Well, I don't know. I cannot give an answer with confidence, but my estimate is that they would have failed the axial force limits imposed by Eurocode 8 if one would have taken into account the additional axial force due to the seismic action according to the analysis. That is not only the gravity, the axial load due to the gravity loads, which were high because of the height of the building itself, but also because of the response of the whole entire building as a cantilever. Outer walls on the exterior, on the perimeter of the building, would have been subjected to a significant increase in axial force. So I would bet that they would have failed the axial force limit. I want to add that the failure mode was so clearly dominated by compression that some experts have even claimed that there was an issue of vertical waves propagating up and down the building due to the vertical component of the earthquake and adding to the axial force due to the lateral vibration and causing these failures. And they based that claim on the fact that such failures occurred even in basements, where the effect of the of bending due to the lateral vibration is much smaller, and these failures could have been explained in basements because of the by introducing the possibility of vertical waves moving up and down the building due to the vertical component. So the issue of the axial force level in these thin walls was very important.
Thank you very much. I would say the conclusion is that the lessons from Chile are not very relevant for Europe and for buildings in Europe. because of the way the walls are designed. I understand. I was in Chile after the earthquake. I've seen those walls. They were designed according to some older versions of ACI 318, and with the case with the low ductility walls and the very substandard, I would say, according to, if you compare it to Eurocode, maybe.
Well, I might say that at least older versions of the ACI code did not pay enough attention to the issue of confinement of walls.
Mm-hmm.
It is important to have a thickness of the wall sufficient for the effects of confinement to develop. Otherwise, the part of the section which remains unconfined because it is too close to the surface is so much that confinement essentially disappears.
Mm-hmm. That's true, and they have not even tried to confine it because the walls were so thin, and maybe who knows what is the reason. But anyways, so maybe given the time, you have been very fit for speaking for 2 hours and 15 minutes. Thank you, almost 2 hours actually. Thank you so much, and I would say that let this discussion continue with you in person, in enjoying contacts with colleagues in Serbia and other things. I understand this is going to be your first visit to Serbia, as
yeah, well, to Belgrade, essentially.
Belgrade. Yes.
Yeah.
So maybe what we can do is we can share these answers to the questions along with your presentation that may be useful for the rest. They will, everybody will be able to hear, to watch the recording, and again hear your answers to the other questions that have been posed. And ma'am, as usual, thank you for agreeing that your recording and your presentation will be available to members of Serbian Association and others on the website. And we have a YouTube channel for the presentation, so it will be like all presentations are on that channel. We are so grateful to you to take time. I know you have very busy schedule right now because of Eurocode, among other things. And we really appreciate the whole presentation and discussion with our colleagues. Branko, would you like to say something as a concrete guy?
No. I just want to thank Professor Fardis for this very nice presentation and the time. And I think that it will be very nice to meet in present all our community of engineers and concrete engineers, which are relying on your books and presentations, and it will be very nice to meet you in person. So we are expecting you in September in Belgrade and Aranđelovac.
Well, it has been my pleasure to be with you today. I very much enjoyed the interaction. Among other things, with the self-confinement due to COVID for 2.5 years, I miss the interaction with colleagues. So yes. I very much enjoyed it, and thank you very much for giving me this opportunity.
Thank you.
Thank you very much, Professor Fardis, and thanks to all participants who stayed until the end and others who have left in the meantime. Thank you and have a good night.
You too. I will send you promptly the file with the answers I was showing.
We will be in touch in the following days. Thank you so much once again. Bye-bye.
Bye-bye.